Okay, hi. We are going to today talk about finding absolute maxes. And it's going to be our first lesson there will be several of these lessons here, because finding absolute maxes is one of the important things in calculus. Before we start, we're going to do a Quizlet. And I'm actually going to record the Quizlet questions so that you guys that are following along at home can check yourselves. This Quizlet will not be for a grade, but we will go ahead and mark it up as if it were. So, our three questions for today, following the same format as yesterday: true or false, give a proof or counterexample. The first question, true or false, is if f of 1 equals 6 and f prime of 1 equals 2, there is a neighborhood of 1 such that f of x is greater than 6. Second question. If f of 1 is a local max, f prime of 1 equals 0. And third question. If f prime of 1 equals 0, f of 1 is either a local max or a local min. And those are your three true or false questions. Go. How about I say for some x in the neighborhood?
Are you collecting this as well? Like what's going on the plain blank paper?
Yep, we can like paper. Now, I'm going to pause this so if you're following along at home, you can work out these questions, and then you can just pick up when you are done. All right, you guys can grade your own. Just mark yourselves up honestly. This is not for a grade, so there it is. First one, if f of 1 is equal to 6 and f prime of 1 is equal to true, there is a neighborhood of x equals 1 such that f of x is greater than 6 for some x in the neighborhood. I recommend to try to get yourself a picture of this. So if we draw ourselves an f so that f of 1 is 6 and f prime of 2, then this would be an appropriate picture for f in the neighborhood. Yeah? And it seems very clear to me that the answer should be true.
Huh?
Yeah.
I drew the picture, but that's a false.
What does your picture look like?
That's right.
Look, there's a neighborhood in your picture.
Yeah. That is fx bigger than 6.
Yeah, look in this neighborhood.
Yeah, neighborhood can be bigger than. But the neighborhood of x equals 1.
Yeah, the neighborhood of x equals 1 means an open set around x
But it can
equals
also
1.
be like smaller than 6.
Yes,
It
that does not contradict that.
a neighborhood. It didn't say.
There is.
Oh, there.
For some x. That's right. I did not say for all x. So
Uh-huh.
be careful about your quantifiers. Some does not mean all. Right, there we go. Okay, now how do we actually prove this? Well, it's actually pretty straightforward. What theorem is relevant to the notion that my f of x has to be bigger than 6?
Oh, I didn't put a theorem. I say because f prime 1 equals 2, which is bigger than 0.
Yeah.
That means it's increasing.
Yes, that's the theorem. You stated the content
I
of the theorem.
forgot the name.
It doesn't have a name. That's good. Since f prime of 1 is greater than 0, and how do we say this? F is increasing. Here's our word through. Yes.
Through the point.
And that's it. So our justification is since f prime is greater than 0, f is increasing through 1, which means there is a neighborhood around such that points to the right are above, points to the left are below, and all those points to the right are above there, as you drew in your picture. Yes?
What about the neighborhood is?
A neighborhood is a synonym for an interval with a center and a radius. So
It's the epsilon.
the open interval C minus delta to C plus delta is a delta neighborhood of C. Okay. Good question. All these questions, like the one Justin just asked, are questions about figuring out the language, and that's really 3/4 of the battle with math. If f of 1 is a local max, then f prime is equal to 0. True or false? False. Give me a counterexample, Justin.
It's like this corner.
Okay. I want a specific counterexample. What could it look like?
That's
Yes, exactly. That works. Any counterexample that has a sharp corner, cusp, or vertical tangent, not a vertical tangent, sharp corner or cusp, at x equals 1 will do. This particular one could be, for example, y equals negative absolute value of x minus 1. So this statement is false, and any counterexample with a corner or cusp will do. If f prime of 1 is 0, then f of 1 is either local max or local min. What do you say? Also false. Give me a counterexample.
X minus 1.
What?
So, Danielle got tripped up by the converse trap. What is our Fermat's theorem? Fermat's theorem, which is that if f of c is a local max or local min, then f prime of c is equal to 0, or f prime of c does not exist. Notice the if and the then here, right? The converse of this statement, if f prime of c is 0 or f prime of c does not exist, then f of c is a local max or min, is a false statement. So the converse of a true statement is not necessarily true.
Wait, what does the graph of I prime point to the concept?
It looks just like that. And so what we actually have here is called a shelf point. And if I were to look at an f prime number line, then the f prime number line shows a positive derivative on both sides, and f prime of 1 is equal to 0.
Okay.
So beware the converse trap. Does that make sense? Make sure you have your if and your then straight. That's why we have to know that strict legal language. You don't want to take any shortcuts. Yeah.
X cubed as a counterexample, since it's the same concept but a different point.
Well, it's not a counterexample for this particular thing because it doesn't meet the condition that's required of that particular thing. For x cubed, f prime of 1 is 3. Yeah, you get moral brownie points. You can spend them on moral brownies. Okay. Very good. Okay. Just show of fingers. How did you do? Okay.
Oh.
All right.
I don't know if that one.
Kind of this.
All right. What did you learn?
The counter example and the first one, like read, like all the words.
Okay. Can I suggest a different lesson for you rather than that? That you read all the words is good, but we need to sharpen that a little bit. Be aware of quantifiers. Some versus all. You interpreted some as all, and it wasn't. What'd you learn?
Be more specific with counterexamples.
Be more specific with counterexamples. Good. Okay, good.
I also the concept, the converse
The counterexample concept. Yep. So the counterexample concept is you're going to create something that meets that condition and it violates the conclusion, showing that the conditional is a false statement. That's how it works. Does that work? Okay, let's talk about absolute extrema and finding them. We talked about absolute extrema already, so I'm going to remind you of the definition and a theorem. F of C is an absolute max of f of x on a domain if f of C is the largest on that domain. Now, I've deliberately used this vague phrase on a domain because the domain could be an open interval, it could be a closed interval, it could be the union of intervals, it could even weirdly simply be a random set of points. It can be any set of points. And likewise, f of C is the absolute min of f of x on a domain if f of C is less than or equal to f of x. And so one of the things that we learned was that the absolute max or the absolute min does not necessarily need to be unique, right? So if I have f of x is equal to sine x, then what is its absolute max value? 1. And how many times does f achieve its absolute maximum value? An infinite number of times.
High time.
Right.
Yeah.
Good job, it's recorded.
Not values of x's.
Hi, Jackson.
Okay. If I have f of x equals 3, then what is the maximum value?
It's just 3 all the time.
It's just 3 all the time. What is the minimum value?
3.
Uh-huh. This suggests an interesting question. If my function is constant, is the max always equal to min?
Mm-hmm.
Yes. If my max equals the min, is my function constant?
Yes.
Yes. Wait.
Interesting. I'm going to ask you to prove that fact as a part of your homework. Here's the interesting question. True or false? Proof or counterexample. If f max equals f min, then f is constant. And I'll let you come in and tell me on Monday whether or not that's true. Okay? Now, we also had a theorem that guarantees absolute maxes and mins. And our theorem was the extreme value theorem. Which again had nothing to do with or. And that is that if f is, what's our condition for the extreme value theorem? Continuous. On a closed and bounded interval. Which I mentioned was the simplest example of this mysterious thing called a compact set. If f is continuous on a closed and bounded interval a to b, then f has an absolute max and an absolute min on that interval. Now, what we like about the extreme value theorem is that it is an existence theorem. It guarantees that there is a value that is a max, and it guarantees that there is a value that is a min. And that is extremely helpful to us under certain circumstances, but it has a limitation. It doesn't find the max or min for us. So without some additional reasoning here, I would be reduced to finding my max and min by walking through the entire interval a to b and choosing each x from a to b and saying, are you my max? No. Are you my max? No. And what's worse is that I wouldn't even necessarily know until I got to the end, so I'd be plugging in an infinite number of values. Surely we can do better than that. We would like some theorems that would help us find our maxes and mins, and as it turns out, we have means within our grasp. This is going to be our first absolute max and min finder. We're going to call this the critical point endpoint theorem. And that is this. If f of c is the absolute max or the absolute min of f of x, on the closed and bounded interval a to b, then one of two things is true. Either c equals a or c equals b. In other words, c is an endpoint. This is the endpoint possibility. Or x equals c is a critical point. That is, f prime of c is 0, f prime of c does not exist. And that's the critical point possibility. In other words, absolute extrema only occur at critical points or endpoints. Is that? No, go ahead. Correct. That's exactly correct. The converse is not true. Okay. Now, why do you think this is true? Do you think we could construct a proof for this?
Start with the local.
Good. Start with the local maxes. How would that be relevant? So, let's start with our if part. Let's start with the fact that f of c is an absolute max. We'll let the min part take care of itself. Is that fair? So suppose f of c is an absolute max.
It has to be a local max.
Does it have to be?
Yeah.
Why? No? Counterexample. Here is my f. Here's my a. Here's my b. There's my absolute max. Not a local max.
Oh, it doesn't really have a look.
You're right. It doesn't really have a local max. So what? It is an endpoint, though. Good point. It's an endpoint.
Oh,
We're
done. To be a local max or endpoint.
Aha! Now you've got the spirit of the proof. You just jump to the conclusion. That is the conclusion of our theorem. Good. But she sees the picture now, and that can help her work backwards to the proof. Good. So the two of you tag team together. Now, can we turn that into an argument? What did you notice logically about what the two of you accomplished or did?
There were two separate places.
Bingo. We're going to call them cases. There were two separate cases. And so a very common math thing is to say case 1, case 2. So which case do we want to have first?
Critical, which is the local.
Look at that point.
And what would be our first case?
With the graph you have over there.
Okay, good. And in this case, we had,
So F, let's say so max out endpoint.
at an endpoint. That's right. So a place to start would be to say, if C equals A or C equals B, then we're done because we've proved, because that case is true, right? If not, then what?
And
The C is a local.
local,
Why does it have to be a local max?
critical.
Because local max only happens at a critical point.
Right, but I haven't noticed that that's part of my conclusion here. It's not part of my given. I'm not given that I have a critical point. I'm only given that f of c is a local, is a max, is an absolute max. And I've taken care of the case where c is at an endpoint. Yes. Ah. If C is not an endpoint, then where is C?
It's in, but
It's
not a closed.
what's she trying to say?
It's
Open
in the
interval, that's right.
interval.
And C is in. There you go. And C is in the open interval. And if it's in the open interval, then what kind of max is f of c?
Local.
Because by definition, that's what a local max is. So that f of c is a local max as well. And what do we know about local maxes?
Occurs on
Critical points. By Fermat's theorem.
Oh,
Good.
yo!
Yeah, that's how it's done. Now, sometimes people feel like case 1 is cheating. So I want to come back and just talk about this a little bit. How can I just assume what I'm trying to prove? I'm not actually assuming what I'm trying to prove. What I'm doing is I'm saying there are two logical possibilities. Either C is an endpoint or else it's not. If C does happen to be an endpoint, that was one of the conclusions I was hoping for, and so I had nothing else to prove. And if C is not an actual endpoint, then I can go on and worry about that other case. Does that make sense? So I'm not assuming what I'm trying to prove. I'm saying I'm taking a state of reality, either C is an endpoint or else it's not. And I'm considering each one separately in terms of the conclusion I'm trying to get to. That conclusion, in the first case, happens to match my conclusion. So I accept it gladly and say, thank you. And in the second case, that doesn't match my conclusion necessarily, then I go on and argue from there. Does that make sense?
Oh, wow.
Yes.
So the route we're doing is proof, right? It's a proof, like. But if it's proof in case 1, you just put C equals A or C equals B, then done. But like, how can you say, like, how do you know the A and B?
That's what I was just explaining. Yeah, it's a good question. That's what I was just explaining. And that is that out of all of the possible C's that I could have, either they happen at the endpoints or else they don't happen at the endpoints. Because I'm restricting myself to the interval A to B. So I say, first of all, let's look at the case where C happens to be an endpoint. Well, C happening to be an endpoint matches the conclusion that I'm trying to make, and so I have nothing else to prove in that case. Now, what if C doesn't match an endpoint somewhere in here? Then I can go on from there and still get the conclusion I want. So I'm taking the world of possible options, C is an endpoint or C is not an endpoint, and splitting that into those two cases. This one happens to match the conclusion of my proof. This one doesn't, but then I can make it. Does that make sense? Yep. So I'm not assuming what I'm trying to prove, I'm just splitting life into. Sometimes we call this a tautology, a statement that's trivially true. Either A is true or else A is false. Yeah. Good. Now, how does this work out in practice? Here's how this works out in practice. Okay. Now, I'm going to start with a question that's easy so we can check ourselves. Find the absolute max, absolute min of f of x equals x squared on the interval negative 2 to 3. You can draw a picture. You should be able to spot it pretty easily. Just visually.
Because I'm doing the
Just visually, I think we can, as checks for ourselves from the graph, we can observe that f of 0 is the minimum value, and f of 3 equals 9 is the maximum value. Okay,
Yes.
we can see that. But how do we actually use our theorem to find those, especially if this function were more complicated? The basic method that we're going to use is we are going to consider the critical points and the endpoints to be candidates for maxes and mins. So we're going to begin by finding the candidates. Out of all of the infinite values between negative 2 and 3, we're going to restrict ourselves to only the endpoints and the critical points as the candidates. And so we do that first by setting f prime of x equal to 0, or does not exist, saying that f prime does not exist. But here, there are no values of x for which f prime does not exist. And now we are going to announce our candidate list. X equals negative 2, x equals 0, and x equals 3. And I just put them in numerical order because. And now we can evaluate f at each one of these candidates.
4, 0, 9.
And the largest one is the max,
It's the 0.
and the smallest one is the min. Nope. The largest one is the max. And the smallest one is the min. Yeah.
4, 4, I'm going to get this last one.
Okay. Yeah, we did do this last year. We're going to do it pretty much the same way. We're going to be a little bit more careful about this part right here. I want you to avoid the newbie mistake. The maximum value is the f value. The minimum value is the f value. It is not the location of that max or min. So these are the locations, and these are the actual extrema. Sometimes people get them confused, and they'll say the max is 3. No, it's not. The max of f is 9 at x equals 3. So the preferred way of stating this is f of 3 equals 9 is max. This is the preferred language because it gives you the max value and the location at the same time. Does that make sense to everybody so far?
Yes.
All right. Well, let's apply that to a weirder function then. Let's take a look at f till 35, right?
33.
Fair enough. Let's take a look at page 227. number 6, in which we are given this interesting problem. A rectangle has its base on the x-axis. This is page 226, number 6. And its upper two vertices on the parabola y equals 12 minus x squared. What is the largest area the rectangle can have?
I remember this kind of question.
Good.
And it's on
And what are its dimensions? Okay. Now, as with many of these things, most of the battle is just translating from English into math. Once we get it into the math, then we can use our critical point endpoint idea to fairly easily find the absolute max. Let's take, first of all, the question that they're asking us, what is the largest area, and translate that into math. How could I? Definitely, area equals xy for a rectangle, absolutely. But here, my point is that I just want to take this word largest here and translate it into a math term. That's right. So what I'm trying to find is a max. Now, we need a sketch of our situation. We have a rectangle. Its base is on the x-axis, so I need to draw myself a coordinate axis here. And the upper two vertices are on the parabola y equals 12 minus x squared. So I need a sketch of that guy. Okay. And that's going to have zeros at root 12 comma 0, and negative root 12 comma 0. Upper two vertices. What's a vertex? Right. So here comes my upper two vertices, like so. And therefore, that fixes where my other two vertices must go because they have to rest on the x-axis. Now, as soon as I have done this, I do not know what the coordinates of this point are, so I'm going to label them as x comma 0. And I'm going to label this guy as x comma y. And by symmetry, it is necessary, yes, because I am dealing with an even function, it is necessary that the y value be the same at opposite points right here. Okay. And now, having done this, I'm going to establish the area in terms of a function of x and y. And what is that area function in terms of x and y? That's it. 2x times y. And this is the equation for my area, but we notice that this equation has two variables in it. And so it is not going to be possible to find its max in terms of two variables with a single equation right there, because there are too many degrees of freedom, basically. So I need to constrain my variables by finding an additional relationship between those variables. And what is that additional relationship between the variables?
Y equals 12 minus x squared.
Bingo. That's exactly it. My constraint is that y can't be anything it wants to. It must be 12 minus x squared. Because y must fit on this curve right here. And so if y is equal to 12 minus x squared, then gosh darn it, y is equal to 12 minus x squared. In other words, equality is a license to substitute. And this gives me now area as a function of x alone, and that function is screaming to be optimized or simple here. And now what I need to do is to find the max value of this function? Derivative. Keep going.
X equals dash 2. Positive negative.
Or negative 2, exactly. And now what? What do these values
And
mean?
the y value.
Well, I'm not quite ready yet. I need to assemble my candidate list first. Don't skip that step. And what are all of my candidates here? What are the other candidates? No, indeed.
0.
I need to consider also my endpoints. What is the largest possible value of x that I can have?
Root 12.
Ah, see, that's the domain of this problem. And the smallest possible value is negative root 12.
How can your area be?
Ah, so what is the area at root 12?
0.
Yes, that's right. Both 0 and both x equals root 12 and x equals negative root 12 form degenerate rectangles that are simply lines. How about when x equals 2? What is the area?
My gosh.
8.
No.
I get 32, 48. And interestingly, also when x equals negative 2, and the reason for that is symmetry. If this is x, then that's negative x, and if this is x, then that's negative x right there. So I have two different values of x that can be the max, but only one dimension. My dimensions are 4 here, and y is 12 minus x squared, or 8 right there. So 4 by 8 does it for me. And this drawing is clearly inadequate. See you later.
Wonderful.